title is Zero is not splitting. So
okay, thank you. Welcome back. So the goal for today is we have 1.5 hours, and we will do, most of the time we will discuss, I will present a seminar essentially, a research seminar on a topic related to the course. But before that, I thought it would be useful to recapitulate everything that we've discussed over the past weeks. Maybe? Is it good to have it open? Yeah.
it's fresh.
Would you like to close?
No.
We like to keep on.
Yeah. Just,
Keep open, please.
alright, it's okay to keep open. Seems to be at least a loud majority to open. So I don't care.
It's fine.
The putting is probably that might be. Well, whatever. Just the part of the chairman can do whatever. You can decide. I just.
Okay, the audience wants to open.
Okay, I just go on with physics. Yeah, and you decide about
Closing out, yes.
Okay, that sounds like a compromise.
Yes.
Okay, so what did we discuss? So at the first lecture, I gave you an overview of systems where you have either symmetry-protected topological phases or where you have intrinsic topological order. And we came to this conclusion of the main points corresponding to symmetry-protected topological phases and intrinsic topological order. And we essentially went through these points during the lecture course by means of examples. So let's go through these again so that you remind yourself of what happened. So in either of these two cases, we have a many-body ground state which has a gap to the first excitation. Okay, there are in principle generalizations from these ideas to gapless phases, but generally what we discussed here were gapless phases. Okay, so then in the symmetry-protected topological phases, we have a single ground state for closed boundary conditions. We saw this, for example, for the AKT chain. We will get there again in a second. And this is distinct from the situation of intrinsic topological order, and we saw the toric code as an example, where we had a ground state degeneracy which knows about the topology of the base manifold, in this case of the torus. Then there is this aspect of the ground state degeneracy is actually intimately linked to the presence of anionic excitations. Because ultimately, these homonyms that we have, this corresponds to bringing like some anions in two different ways around each other, and this gives you a minus sign, and is the reason ultimately for this ground state degeneracy. These 2 points are actually intimately linked. For intrinsic topological order, you cannot connect this ground state adiabatically to vacuum. That means that you have to go through a phase transition and gap closing. For the symmetry-protected topological phases, the word symmetry protection refers to the fact that as long as you keep the symmetry, the same is true. You cannot go from this topological phase to the non-topological phase without closing a gap. But if you break the symmetry, there are trajectories in parameter space where you can do so adiabatically without closing a gap. Okay, and then this was sort of a solid state physicist perspective on this, but there's a quantum information version of the same statement. So intrinsic topological order is long-range entangled in the sense that if you start from a product state, there is no finite left unitary circuit that can produce such an intrinsically topologically ordered state. And in the case of symmetry-protected topological phases, there are only such finite left circuits which bring you from a product state to a symmetry-protected topological phase, only such circuits which do break the symmetry on the way. Again, it's essentially the same statement, just in terms of quantum circuits rather than tuning parameters in a solid state experiment. The characteristics of symmetry-protected topological phases are edge states, and we just discussed those from various perspectives. Here, the edge states are sometimes there, but they're not necessarily there. So, the examples that we use to discuss this, and I want to just flash everything that we discussed on a sort of mind map where I introduce models in circles and concepts and theoretical tools in squares. So, symmetry-protected topological phases that we discussed fell into 2 categories. bosonic and fermionic, and I gave an example for each of those. So we started out with the 1D transfer field easing model. That's of course a symmetry, an example for spontaneous symmetry breaking at zero temperature. Spontaneous symmetry breaking here being the appearance of long-range order of what we call ZZ. These phases here, I mean, a major point about them is that they don't break any symmetry of the system. These are different patterns of self-organization of quantum-manipulated systems which do not assume spontaneous symmetry breaking. But the 1D transfer field easing model, in particular the symmetry broken phase, is dual by means of a, or is related to by means of a non-local transformation to the topological phase of the Kitaev chain. So what we did is we mapped the 1D transfer field easing model to the Kitaev chain. We also discussed Kramers-Vannier duality, but that's something slightly unrelated. And what we saw is we mapped this problem onto free fermions, and we discussed the free fermionic model with closed boundary conditions and solved the problem by Fourier transform. And we saw that the bulk has a topological invariant. Remember, we had a mapping from the Brillouin zone to something which was essentially the two-plane with the origin removed, and there were contours which were enclosing the origin and contours which were not. These were topologically distinct phases. That's the bulk invariant that you can use for free fermionic systems by studying the mapping from the Brillouin zone to a certain parameter space corresponding to the Hamiltonian. This came along with edge states, and we solved for these edge states explicitly. In particular, we went to the limits of the phase diagram where, in particular, one of those two limits, there were these unpaired Majoranas at the edges of this chain. Then using this, we introduced this concept of symmetry fractionalization. So in the case of the Kitaev chain, there is a fermionic parity as a symmetry, so fermionic parity is conserved. And this symmetry fractionalizes and has a non-trivial projective representation at the edges, in this case of fermionic type. Okay, so we introduced this idea of symmetry fractionalization and then used it to generalize the classification of free fermions to a classification of interacting systems. So we didn't discuss this in great detail, but these bulk invariants, they go, I mean, there are different symmetry classes, and various symmetry classes you can have different types of topology. In this case, this would be actually, if you have time relative symmetry, any integer number. So there is infinitely many topological phases for free fermions with parity symmetry and universal symmetry. But then we studied from the perspective of symmetry fractionalization how these two symmetries that I just mentioned can be projectively represented at the edge. And we found that there are only 8 phases, which is indeed known that interaction effects reduce this Z classification down to Z8. Then we switched from fermionic to bosonic, and we discussed antiferromagnetic spin chains, and in particular we discussed the AKLT model, which is a soluble model for spin 1 chain with somewhat weird interactions, includes fine-tuning between the Heisenberg antiferromagnetic interaction and the biquadratic interaction. When this is fine-tuned, you can actually solve this problem exactly, and we've done this. We found edge states. We had actually previously discussed what are the various ways of represent a subgroup of SO3 with these projective representations at the edge. And the AKLT model also served as an example for a matrix product state. So this is not necessarily related to the idea of topologies, but I wanted to highlight it here. It's a tool that I don't personally use, but it's used a lot in the community to describe quantum many-body states, in particular in one-dimensional. After that, we switched away from symmetry-protected topological phases and we moved towards intrinsic topological order. And we sort of started analogously to the case here. Instead of starting from the 1D transfer field easing model and doing a Kramers-Vannier duality or essentially a Jordan-Wigner transformation, Here we did the Kramers-Vannier duality of the transverse field Ising model. So it's not a duality, but it's Kramers-Vannier mapping, and what you get then is a Z2 gauge theory. That's the work which you mentioned by Wegner. And is of course related to the toric code, which was proposed in the context of quantum information theory. Then we studied the toric code at length. We found its ground state, which is of course very strongly entangled. And we found the anionic content, so these are particle-like excitations on top of the ground state, which are local. So the E and M particle, or also called, second one also called meson. And we discussed how they fuse. We discussed how they break. Particularly, we saw that the molecule of E and M, called epsilon, for example, in annotation, that this is a fermion. And then we discussed topological ground state degeneracy, which is essentially a consequence of these anyons corresponding to creating two M particles out of nothing, bringing them across, annihilating them again, and then looking what happens to create a pair of E and go in the other way. Okay. We then switched from the plain toric code to fermions coupled to the toric code, or fermions in the gauge theory. In this context, we discussed Fermi surface reconstruction without spontaneous symmetry breaking. So we had an example where we had two different phases of this problem of fermions in the toric code. These two different phases had very different Fermi surfaces at the same affinity. One phase was effectively the ground state with 0 flux in each plaquette and made a big Fermi surface. One phase had effectively 5 flux in each plaquette and a small Fermi surface, 0 knots. Neither of these two phases broke any symmetry, so this motivated to actually distinguish these two, and generally to discuss a little bit how to distinguish different types of topological order. And again, we resorted to projective representations of symmetries. In this case, we studied how certain crystalline symmetries are projectively represented when they impose only modular gauge transformations. We also discussed how it's possible to have a Fermi surface which apparently violates the plain vanilla version of Lagrange's theorem. And we re-derived Lagrange's theorem from a topological perspective by a flux insertion argument with Oshikawa. And then also discussed how this flux insertion argument is altered in the presence of topological order of the type that we just discussed previously here. Then we concluded yesterday and the day before. We concluded going back to bosonic SPTs. We went back to antiferromagnetic spin chains and derived the topological field theory. So we discussed first of all the field theory of single spin. In that context, introduced a certain type of topological term called the Sumino term. That was the term that measures the spheric phase. And we found that actually, due to topological reasons, the prefactor of this term is quantized. Then we switched to the spin chain, in which we sort of derived the effective action for the 1 plus 1 dimensional field theory, and found a different type of topological term, theta term, which measures the number of fermions in the system. And we discussed how this number of fermions changes the low energy physics and this Haldane conjecture, which states that spin 1 or integer spin chains are gapped, but half odd integer spin chains are gapless. So this is what we discussed, and if you wish, we can take questions on this. Then, this was a little reminder. Lecture notes are online. There is one more chapter in the lecture notes that I didn't manage to cover, which is Schulz-Montes theorem. It's essentially a proof that spin 1/2 chain is essentially gapless. It has an excitation which is 1 well above the ground state. Okay. All right. Then let's switch to existentialism. Zero is not nothing. And I'm going to talk about topological Green's function zeros, specifically concentrating on a model similar to what we discussed in the lecture course, an exactly solved model of toric hold time. But I wanted to also spend some time to discuss this field of research a bit more generally. So what is it about? So what are Green's function zeros? So this is the Green's function. V is complex energy. K is momentum. In a free system, we will use fat G for a full Green's function in an interacting system, and non-fat G as the Green's function in a non-interacting system. So in a non-interacting system, it's just a resultant of Hamiltonian, for example, for a single band. This is just Z minus epsilon of K inverse. And of course, what we study is the poles of these Green's functions. For example, here you see the spectral weight, the imaginary part, let's say the retarded Green's function. And whenever this is lit up, that means that you have an excitation that corresponds to a pole. Now, in interacting systems, the Green's function is more complicated, but still you can ask a question about just a two-point correlator. And a two-point correlator has all of the interaction effects shuffled into a function that is called self-energy. It's also a function of energy, complex energy in K, if you have translational symmetry. And now we can be situations where the self-energy has poles, which means that the Green's function is zeros. And then you can start to ask this question at each point in energy versus momentum, and trace the zeros of the Green's function. So then you get something of this type. So here in red is the position energy versus momentum, where the Green's function is zero, and under very mild assumptions, these zeros form also continuous bands, just for the same reason as poles form continuous bands. And then you can ask the question whether these band of zeros, whether they can be topological. Topological in the sense of band structure topology. And when does it happen, and what does it typically imply? So before getting to all of this here, I thought it would be useful to remind ourselves, well, or maybe this is for some of you also new, when we have zeros in the Green's function. And I'm going to give you some highly non-trivial examples, and I'm giving you some highly trivial examples. But at least we get used to it. Okay, so my understanding of why this is interesting and why the community started discussing zeros is related to the problem of Fermi surface reconstruction and Lagrange's theorem. So this is something that I briefly mentioned in the context of the lecture course. I showed you briefly the phase diagram of the Cook rays. This is temperature, this is doping. The superconducting dome here is the dashed line. The important bit here is this yellow region, which is the pseudogap region. In the pseudogap, ARPAS just shows, this is schematic, but essentially what ARPAS shows you. In the Bern zone, you just see the spectral weight at these arcs. And it's generally believed that the spectral weight closes up behind here in the small ellipse. However, so P equals 0 corresponds to half filling, and then this region is like half filling plus a little bit. What you would expect actually is a Fermi surface of this type, which is covering about just a little more than half, or more than less than half of the Bern zone. Well, this here just covers a very small fraction. So,
Sorry. If you have these joint pieces of arcs, how do you define what?
you might not be able to see this, but I tried to draw faintly behind the ellipse closure.
You can switch on the light.
Which light?
The right mode. The right mode.
Yeah.
You can switch off all of them, and then yeah.
Can you see it better?
I see.
But it's of course a problem. I mean, in experiment, they really just see such arcs, and the spectral weight from back here is very, very faint. So it's hard to really get it. But the belief is, I mean, we do believe that the Fermi surface is something, a closed contour. Okay, so. But even this, but what I want to say is that these small x here, these small ellipses, they are too small. They don't suffice Lagrange theorem. And another way of seeing it other than Arbus is, for example, if you look at the Hall coefficient, so this is the Hall number, so that's the one of Hall resistance. At small doping, it follows, it's just linearly proportional to the doping, and then it jumps around here at T star, and then it starts to follow 1 plus doping. So this line here is the one that you would expect based on such a Fermi surface, corresponding to the number of mobile carriers 1 plus p. It's just p above half filling. Half filling being one electron unit. Here you have somehow 1 too little fermionic carriers, mobile carriers. And one way to try to address this is the following. We get to there also later again. There are various ways of writing down Lagrange's theorem. We saw one that we derived in the connection course. This is another one which is actually more close to the original one. There is a term called Lagrange integral, which I'll get to later. But then there's this term which is essentially the area in the Brownian zone where the zero energy Green's function is positive. So you can change this area either by poles or by zeros. So what I want to say is that zeros in the Green's function, particularly zeros at zero energy, are a way to sort of find another loophole in Lagrange's theorem. Okay, so this is one reason to study Green's function zeros. So this is of course a problem in strong correlations. To be honest, our understanding of this is not so great because it's very complicated and very complex. So let's do something much simpler. Let's look at a particle in a periodic potential. This could be either a crystal or it could also be a density wave, charge density wave. Maybe in the context of the loop rate, it's a spin density wave. And of course here you see a replicated extended zone scheme of the model. So we have here shifted these parabolas by reciprocal lattice vectors. In the case of pi antiferromagnetic order, it corresponds to shifting this thing here by order. And then you can do you can pretend that you never heard about Bloch's theorem, and you just calculate the self energy, taking into account resonant scattering between parabolas. And now you can sort of scatter between scattering between parabolas corresponds to giving away one reciprocal lattice vector. So you go from black parabola to orange and back. And if you do this at this energy here, you will get a pole in the self energy because there is another excitation at the same energy. So the self energy pole then looks like a zero in the Green's function. Of course, this is ridiculous because everybody of you knows Bloch's theorem, and you can just do Bloch's theorem rather than doing this procedure. But at least you get an idea that resonantly scattering into a certain other fermionic mode that happens to live at the same energy gives you a zero in the Green's function. And why is this relevant to this business here? Imagine you look at this for an antiferromagnet, so you start with an AL state, and then of course you have a sort of a doubling of the unit cell. And what you get, of course, also on the, if you take this into account, here these degeneracies will be lifted and you get a self energy which looks at this time. But now you want to ask this question in the absence of spontaneous symmetry breaking, so you crank up the either thermal but in particular also quantum fluctuations. And so when you now sort of start from the situation where you have this density wave, but then you start to include quantum fluctuations of spin fluctuations, and where you end up is when you're in half filling, so in the instantly case, you end up in a quantum spin liquid that I didn't manage to cover, but Ulrich Messner will give you some intro to that. Or when you're at slightly above half filling, you get the Fermi surfaces of this type. So one strategy to sort of explain these weird too small Fermi surfaces is, philosophically speaking, essentially something like looking at quantum disordered antiferromagnets. Let me give you something even simpler, which is just, so these here were like bulk systems here. But let's go to a single impurity. Even there, we have, we have Green's function zeros, which sort of could be somewhat trivially, but it's good to remind ourselves. So here you have a half half-infinite chain of green P's, and then you have here a pink dot. This is the resonant level. So these are all non-interacting fermions. Fermions can hop from side to side, and then there's also hopping, maybe with a different amplitude called B here between pink and the first green side. You can calculate the Green's function on this green side here, and the resummation of hopping here and back gives you a Green's function of this type. And obviously, when this GF is resonant, so that the energy when Z is the energy of this level, you get this is the green, is the self-energy. You obviously get a pole in the self-energy. It's a trivial statement, but still you see that in this case the local Green's function carries a pole, which is just reminiscent of the fact that there is a resonance somewhere else. Okay. This looks like something I would say rather trivial. But here's an example which I believe is maybe similar physics, but it's very hidden. This example here is the quantum impurity problem. So you have this here now is this half chain here now is a metal, a one-dimensional metal of spinful fermions. So these fermions can hop from green side to green side. They carry spin. And then the quantum problem is you put on this pink dot here, you put just a spin. Not a fermion, just a single spin. So here the Hilbert space contains two species of fermions up and down, and you can have them empty of fields, so it's four possible states. Here, this here is just a cubic diffusion. So you have only two states here. And then you take into account antiferromagnetic spin-spin interactions between this moment and the magnetization on this side. This model is, of course, a fruit fly model for many-body physics. We've discussed it over many years. We know how to solve it in various ways. And one way of solving it is actually using field theory and then mapping it back onto the resonant level model. So you can actually map this model to this model here using a non-local transformation. So the basis change is really non-trivial to do that. But then once you've done the basis change, you end up here. Then you understand that sort of the Green's function zeros that you have here, they're related to essentially also Green's function zeros in this. So here, this is just a spin, and we're mapping also the spin to a fermion, but the fermion is emergent. So while originally here, in this case here, you get trivial Green's function zeros because you hop from one fermion to another fermion in bound states. Here you have to do this mathematically, this non-local transformation, and at the same time, philosophically, these are emergent fermionic excitations. And you can go further from a single Kondo impurity to a Kondo lattice. So now you have maybe a triangular lattice and electrons moving around freely in the lower layer, here in red. These are electrons which move around. And then you have local moments everywhere on this yellow lattice. And it turns out that for such Kondo lattice models, also you can use some emergent fermions, these spins being represented by fermions, to end up with zeros in the Green's function of the red fermions. And let me also emphasize that these Kondo lattice models, I briefly mentioned this in the lecture course, they also, so such materials which have such Kondo lattice models, they also realize similar phenomenology as the cuprates in terms of this Fermi surface reconstruction. And again, something like violation or apparent violation of that. Okay. Now, what I could do now is I could discuss with you various categories of Green's function zeros. This is somewhat, I don't know, what's the gist? Did you get an idea of, did you understand a little bit? Do you have a feeling for these Green's function zeros? Do you think this is totally nonsense? Do you think it's always trivial? Any comments? If you don't have objections, I mean, if you think the Green's function zeros are okay, you can just skip this. This part here is an attempt to categorize when I believe that these Green's function zeros are interesting, and when they're not. I propose to do the following. I go to the main part of the talk, and if afterwards you think, what the hell are these Green's function zeros, we come back to these slides. So there we go, sorry. So this is, now we're going as I said, we're discussing Green's function zeros, and in particular, we now want to ask whether they can be topological and what's their impact. And I wanted to give a little bit of an overview historically how this has emerged. The first person who has really discussed this seriously was actually more than 10 years ago, Victor Ferrari, who studied interacting topological insulators, and for these interacting topological insulators, discussed topological invariance, and in particular also discussed the impact of Green's function zeros. So, topological insulators appeared like in the late 2000s. This is early 2010s, when people moved to sort of more complicated things than free frameworks. And then this has been lying around for a while, but has had a very strong resurrection in the last year. So here you see a couple of papers, which are mostly numerical, in which Green's function zeros are discussed. And not only zeros in the bulk as a band structure, but also the implications on the edge. So we will see this in a second. There's a bulk boundary correspondence for zeros, analogously to bulk boundary correspondence. Here you see a more fundamental kind of work. So what is mostly numerical? On the right side, you see the discussion of Green's function zeros in the context of more or less abstract discussions. Everything is this or last year. So there is this topic of symmetric mass generation that we briefly touched upon. So remember, I discussed with you this eightfold classification of interacting topological superconductors. And I briefly mentioned that when you have 8 Majorana, so you have 8 chains, and you get these 8 Majoranas interact, there is a way to create a many-body gap which doesn't break any symmetry. And this question has been generalized to imagine you have a three-dimensional topological insulator, which has a Dirac cone on top of it. And you can ask the question whether you can gap this Dirac cone without breaking any symmetry. And this is a similar discussion as the one of the edge states here. If you have a certain number of Dirac cones, they can form a many-body gap which does not break any symmetry. These many-body gaps are typically not corresponding to water parameters in the set. There is no symmetry breaking. So there's no fermionic bilinear that opens the gap. Instead, the electrons form, for example, bound states of 4 electrons. And this is, of course, this is a topic that is of interest sort of to more fundamental research. Here you see Kyrner escape theories, where they also discuss propagator zeros, or they discuss the impact of Green's function zeros on the quantum field theoretical anomalies. So you can calculate this triangular diagram for AET anomaly and ask the question, what's the impact of zeros? On the left, you see sort of more solid state-oriented questions of the same type. So these anomalous diagrams, they're oftentimes related to topological response functions. We will get, for example, to the Hall conductance. And there is a question here, what's the impact of zeros on these? And actually I will present this in the next slide. Then there are models that are discussed where these Green's function zeros appear. So the models that appear, that were discussed, one of them is actually generalization. You can take these 8 Majoranas, you can make quantum dots of 8 Majoranas at each dot, and then sort of let them couple. That's a way to get a lattice model of Green's, which has Green's function zeros. So you sort of seed the Green's function zeros locally by taking a model from which you know that it has in the local Green's function zeros, and then you sort of couple each dot of this type, and then you get a dispersion relation of these zeros. That's what's done by Yishuang. I'm not sure exactly if this is also in this paper or by previous papers. Here, and I wanted to show this to you because it's a method that is used quite a lot these days. I personally what do I want to say? I mean, it's an interesting model that is used in these papers here down left. But the model has very serious limitations that one should just be aware of. But by itself, the model is interesting. These are models to describe mod insulators. So we're discussing Green's function zeros ultimately in correlated systems, right? So to get a Green's function zero, we want to have the zero of the real part of the Green's function and of the imaginary part of the Green's function. When the imaginary part of the Green's function is zero, that means we have a gap. That's what we call a gap, right? I mean, when there is a certain window in which the imaginary part of the Green's function is zero, that's what we call a gap. So for sure we want to have an insulator. And there is a simple model for mod insulators that has been generalized into topological case. Let me write it down to the simplest things. These models are called Komoto-Hatsugai models. And they look like this. Simplest example. So sum over all k, C dagger k, Ck, psi k. This is some spurious relation. This is 3 fermions. Let's assume that these fermions are spinful, for example, to describe something like a mod insulator. And then what's added is an interaction. This interaction is local in k space rather than making it local in x space.
Maybe it was light or
Maybe I could like. These are these Komoto-Hatsugai models. These are on the left. You see generalizations of those. I want to briefly mention those, given we discuss them a lot. This is a simple model actually for a correlated insulator because you can solve it at each k point separately. You find the energies of the empty, singly filled, and doubly occupied states on each k point. And then from this you will find actually quite easily that when depends on u over t, or depending on the model, actually even infinitesimal u, you open up a gap which is a many-body gap. So it's a neat model to understand mod insulators, but obviously it has very serious limitations, in particular when you want to discuss topological phases. Because this model is local in k space, so it's ultra non-local in x space. So when you have a model which has very non-local interaction in x space, there are two questions which arise, which are a complication. First question, when you have topology, you want to ask a question about edge excitation, so you have to somewhat terminate the system with infinite range interactions. So that's a weird thing. You don't really know how to do this. And the second thing is, when it is so long range interactions, you have to do Biot substitution, not only with the hopping term, but also with the interaction term, to calculate transport coefficients, let's say linear response or whichever transport coefficient you want. So while it gives it has some neat aspects of very quickly and easily getting phenomenology similar to, let's say, Howard model physics. There are limitations of these tractable models related to the non-locality of the interaction. Therefore, what I'm going to discuss with you is how to get these topological Green's function zeros out of the Tory code. And that's all. Okay. Now, I want to go back to Landa's theorem and discuss with you maybe the more standard way of seeing the Landa's theorem. So here, what you see here is the density. And the density is usually just the integral over the Green's function over, in this case, frequency in the imaginary time formalism. So this is imaginary time formalism in this case. And over the full Breuer zone. And then I've split this integral into two parts. So I've used that, you can always, I had this before, G inverse full of Z and K is G inverse of Z and K minus sigma of Z and K. And this guy here is just Z minus H of K. This is the single particle Hamiltonian thing that enters the bilinear of the fermions. Z is I epsilon in this case. So when you take the sum of this guy here and this guy, the only thing that remains is the g without the boldface thing. And the epsilon derivative of the g without the boldface thing is just I. So the sum of this plus this gives you just in the integrand trace g. That's just a density. But this is common to write it this way. So there is this contribution here, which is called the Lagrange integral. It can actually often, I mean, at least in sufficiently weak interaction systems, it has no contribution at all, but it can have a contribution in principle. And then this first part here is actually topologically invariant when you have an insulator. In the metal, this guy here gives you a standard expression of Lagrange's theorem, which essentially tells you that, so forgetting about IL, essentially it tells you that the density is given by the area enclosed either by zeros or poles in the ground zone. You see that there is a duality between zeros and poles because there's duality between G and G inverse. I do one partial integration and G inverse and G swap positions. Once they swap positions, well, what was the role of the pole becomes the role of the zero, and what was the role of the zero becomes the role of the pole. So this object has, in a metal, it gives you the area enclosed either by Fermi surfaces or Lagrange surfaces, which is the surface of zero. In an insulator, this thing is actually topologically invariant. Topologically invariant related to the mapping from energy momentum space to the manifold where the Green's function lives, which is the general limit. And this topological invariant in an insulator measures the number of filled bands. It's a very simple invariant. It just measures how many bands you fill. And therefore, it's an integer. Okay. So that's Lagrange's theorem. Now let's go to the Hall response. And the Hall response can be calculated in the simplest case just by using thermodynamics. That's the Wiedemann-Schläger formula and applicable to these insulators. If you add a magnetic field to your system, you calculate the density in the presence of a magnetic field, and you take the derivative with respect to magnetic field at b equals 0. And now you do this with these two terms. Get rid of this. The second term here is just this guy here, and as I said, it sometimes has no impact at all, or actually we will see a situation where it has an impact. And then from the first one, from this N1, you generalize, you get a different topological invariant. In particular, in 2 dimensions, this is a very simple interpretation. And it's a combination of, in this case, 3 such G inverse, partial derivative G, G inverse, partial derivative G, G inverse, partial derivative G. We are taking here, this depends on the direction of the field. Let's take for simplicity a 2-dimensional system. So D equals 2. Then this is just cycling over mu, nu, and rho are cycling over kx, ky, and epsilon. Again, you see the duality between zeros and poles. Actually, I should say that this formula first was written in this paper by Ishikawa and Matsuyama, but mostly I knew it, and I think most of the community knew it from works by Volovik. For the case of free fermions, let's say in 2 dimensions, this guy goes back to the integral over the Berry curvature over the ground. But it's of course generalizable to interacting systems, and when you ask the question about the quality of interacting systems, then this is a useful quantity to study. Let me emphasize that sigma Hall and N3 are not exactly the same. There is this additional thing. And the difference between N3 and sigma Hall, so imagine you draw sigma Hall as a diagram, and you ask yourself, should I just replace the Green's function by the Green's function with the self-energy? The answer is that's not necessarily enough. There may be vertex corrections, and the vertex corrections are hidden in this high level. In particular, you can study N3 for a very simple phenomenological self-energy of a Mott insulator. So the self-energy being just U squared over Z plus some Hamiltonian H little of K. So maybe you have originally Hamiltonian H of K, but then you do like, maybe you do dynamic mean field theory, so you derive an effective self-energy somehow, clustered in a field. And then you get, this is a very typical expression. And by the way, I should also say that, I mean, my collaboration with these gentlemen here, they are coming from the dynamic mean field theory community. So these are numerical methods which are Green's function based to determine the physics of Mott insulators. And for them, it's very natural to write down or to obtain such self-energy. But what turns out is that you have a Hamiltonian plane, like in the Green's function, there is a part, in the Green's function, there is this part. So maybe to make a connection to this notation, I will call this here H twiddle, AH. And as we just saw, this guy here is U squared over Z plus H twiddle. You can put such a Green's function into this N3 and see what is determining the topology. Is this N3 quantized because there's topology in H? Or is it quantized because there's topology in H twiddle? And it turns out that H twiddle entirely determines N3. The H's give the dispersion to the Hubbard bands. These are bands that in the imaginary part of the Green's function appear at energies of the order of U. But their topology doesn't enter anymore at all. Only the topology of H twiddle enters. So the topology of zeros entirely determines N3 in these simple nodes. Okay. Alright. So as I said, the zeros entirely determine the topological invariant. Does this imply that by bulk boundary correspondence you get zeros at the edge? So instead of having an excitation at the edge, you could have the zero at the Green's function. So instead of having a pole at the edge, you have edge. So to illustrate this, here we have this Zu-Schrieffer-Heger chain plus Hubbard U. This is a one-dimensional model with alternating hopping strength. So you hop from side 1 to side 2 with T, and then from 2 to 3 with T prime, and then from 3 to 4 again with T, etc. And it has two different topological phases. I mean, one topologically trivial phase and one topologically non-trivial phase. The strict wording is actually not topological phase, but atomically obstructive phase. Long story short, one expects in the case of non-interacting fermions edge states in the topological phase, and that's what you can see here. There are edge states illustrated by these blue things. And what you can see on the right is when you add the Hubbard U, you see these red bits. And these red bits are actually edge zeros. So the Green's function has zeros localized at the edge, which are a consequence of topology in the presence of strong interactions and zeros. What's actually plotted is the weighted eigenvectors of the Green's function. So you take the Green's function, maybe you make a Hermitian, then you look for its eigenvalues and its eigenvectors. The eigenvectors are vectors in particular also in real space here. And then what you plotted here is plotting the eigenvector, maybe modulo squared, weighted with the eigenvalue. And when the eigenvalue is 0, you get these things. Okay, so what we've seen is that there is not only you have not only the possibility of having poles at the edge, when the Green's function is topological and has topological zeros in the bulk, you can also have zeros at the edge. And now the question is, when you take two usual topological insulators next to each other and you glue them together, usually you have two edge states which meet, and these edge states can hybridize and gap out. What happens when you take zeros, a model which is a strongly correlated topological insulator, and you put it next to this guy here? And here is, oh, by the way, these are the bands of poles and zeros that I mentioned. When you glue these two together, it turns out that a zero and a pole can mutually annihilate. So at the interface here, so what's done here is, it's of course a numerical experiment. Half of the system is strongly interacting, that's the right half. This half here is non-interacting. On this left end, we therefore have a pole in the Green's function localized at the edge. On this right end, we have a zero of the Green's function localized at the edge. And here, zero and pole have mutually annihilated at the interface. When I first saw this, I was quite surprised actually. Okay. So these edge zeros apparently, so we have, this is the first physical consequence that we really see of these zeros. Zeros in the Green's function have the ability to annihilate a state when you put a topological interacting system next to a topological non-interacting system. The other thing is, you can ask this, and this is now based on the phenomenological model, you can ask the question, what happens when you have a wave packet traveling along the edge and then encountering edge zeros? Yeah, so what we have here is, so usually you have, in this case you have the topological insulator. Usually you just have maybe a chiral edge state, or what we did actually was helical edge states, so it's a quantum spin model. And well, these edge states are topologically protected. They have to be there, and the motion along the edge has to continue. Now there's a question, and that's what's shown on the left. If you put here a triple mod insulator, nothing changes. Sorry, that's good. But when you put here such a topological mod insulator, one which has zeros running around, these zeros can actually zeros which run the same way. It doesn't really matter. There are zeros running in the topological insulator. Sorry, they're running.
Can you turn on the light?
Yes, I'll do that.
The camera is not recording this part of the.
But it's only used for expert explanation. I mean, most of the action is going on the screen. It's just an additional. It's just a picture of what's drawn up there. This edge state can annihilate with a zero. And that's what you can see in the simulation here. There's a wave packet, so there are different times. What's shown is different times.
Could you explain please how to relate the motion of zero Green function and the motion of wave packet?
So we don't really know how to excite zero. What we can do is we can inject a wave packet. So red is the part which has extra excitations. We can inject a wave packet here. And what I'm saying is that this wave packet hits this area where there is a zero, and then the wave packet disappears. Because it has annihilated the zero. So you need to look at this. Now, what is actually plotted? This is essentially using the Green's function. So the self-injected Green's function we had, it's just the dynamics of this wave packet that is sort of inferred from this simple phenomenological model. I think it's quite great. There are lots of questions arising from these zeros. I think these zeros are a very deep thing. And maybe give you a little bit of more background on the work that my collaborators have continued separately. They've actually studied the model with an approximate method based on some state bosons, and they relate the zeros to the appearance of purely spin excitations at the edge, which do not carry charge, but they are sufficient to sort of decohere the spin part of this guy. So, okay, first of all, they looked at a quantum spin Hall effect. So in that case, we have two quantum propagating channels with opposite spin. One of them is spin up, the other one is spin down. And you can look at, so there is charge and spin degrees here. And at least in the simplest slave boson mean field picture, what this topological insulator, topological model insulator has, it does have an excitation at the edge. So the story is a real excitation. But only in spin space, the charge excitation is frozen out because it's a model insulator. And then the spin excitation can cancel the spin excitation that's coming in here. Then only the charge survives, but what we are studying here essentially is the wave function of fermions. And fermions have both spin and charge, but if the spin part is equal here to this guy here, then you cannot see anything with the fermion. But anyway, so the zeros are weird. And since zeros are weird, we decided to study this using a model very similar to what I presented in the lecture course, namely fermions coupled to the toric goal. So the goal was to see whether we can find Green's function zeros in an exactly soluble model, or at least in a regime which is in a controlled perturbation theory around a soluble limit, without using something which has long-range interactions. And what we did is we just studied the toric code coupled to fermions. So we had this before in the lecture course, but now it's on a hexagonal lattice. Same notation as in the lecture course, B's and Q's. So on the hexagonal lattice, we have a plaquette operator. It doesn't come out very nicely here. This is green. This plaquette here corresponds to the product of all of these around the plaquette. Here you have now on the hexagonal lattice, you have two star operators. One which has the orientation like in the Mercedes logo, and one which has the upside down Mercedes logo. Here. So these are now a product of three axes around a given site. That's the standard code. And now you see that you have per unit cell you have two stars and one plaquette. And per unit cell you have three qubits, 1, 2, 3. So you have essentially again the same number of particles of motion as you have degrees of freedom. And importantly, each plaquette and each star still share 2 qubits. So the argument that we have for the square lattice holds here 2. All q's and b's commute, and we can construct the ground state in the same way as we did in the lecture course. So the reminder, you start out by making the b stacky, all the spins point up, and then you project it 1, 2, 2. Okay, so we discussed this. This is a topologically ordered state, and there are two types of excitations: e particles and m particles. Their energy in this notation here is e particle has energy 2h, and m particle has energy 2k. We will not need these m particles at all. The e particles will be important, but we can send k to infinity. So in everything that I say, k is essentially infinity. And now what's added here is a topological band structure of fermions. So the fermions are similarly to what we did in the lecture course. They're hopping around, they're sitting on the sites, and now the hopping that we have here contains three terms. One of them is the standard nearest neighbor hopping, from, let's say, green to blue, but hopping with this z operator on the link, as we had it in the lecture course. Then there is a next nearest neighbor hopping. Sorry, there's also a staggered potential. This is on site, so blue and the green have different energy, onset energy called W naught here. Then there is a hopping which is next nearest neighbor hopping. This is a model that was introduced by Haldane in the late 80s to create a quantum Hall effect without Landau levels. It's what's called now the Chern insulator. So this model, without the toric code bit, has a dispersion relation which has, we show this. Maybe I should just show them the main aspect of this in the Brillouin zone. So the Brillouin zone of this model looks like this. That's a triangular lattice. Brillouin zone is hexagonal. And then if you have just W1, that corresponds to graphene. You just hop from side to side, and graphene has when you solve this Hamiltonian by Fourier transform, you get here and here two different Dirac cones. One of them goes this way, and one of them goes the other way. What's plotted as it is. Then, so that the degrees of freedom pseudospin that enters in the Dirac cones is a sublattice potential, right? Make remember this, those of you who ever solved graphing. These are spinless fermions, and the Dirac equation here is something like P dot sigma, but sigma is not spin, sigma is a sublattice degree of freedom. Then this W naught is a staggered sublattice potential, which just adds W naught sigma C. This all opens again here and here. Trivially, this is a topologically trivial gap. It has no impact. You can go to the atomic limit by just taking everything to 0, except W naught. You will not go through a phase transition. You will just end up in a situation where you have atomic instability. So that's the boring mass term, but it's also a mass term that we've added. And then there is another mass term which has the form. Okay, so maybe I should write it. This is actually something a bit more complicated. There's another mass term which, in the K and K prime values, that looks like this: plus or minus W1, sorry, W2 sigma Z. So there is this next nearest neighbor hopping has higher harmonics in the function of K's, and adds a term proportional to sigma Z, because it is intra-sublattice, but it has to be diagonal, and it has alternating signs, and in particular it has opposite signs in K prime and K1. Opens a gap, but opposite in sign, and this guy opens a topological gap. And in particular, it gives you sigma Hall equals, depending on the sign of W2, it gives you E squared, 1 E squared. So that's the Haldane model. Okay, and this model is still soluble, at least essentially. And in the limit case, infinity, the model is actually really exactly soluble. And we proceed the same way as we did in the lecture course. So we start out by making the B terms happy. Then we realize, sorry, this is the information about when this term wins over this one, you have a topological instead. Okay, there is a factor of 27 that is not taken care of here. Okay. So the Q's and V's are still integrals of motion because of this parity term here, also the hopping terms don't alter the conservation of Q's. And then the ground state is given by this product of solving this problem in a given gauge, let's say all up. In this gauge, this Hamiltonian goes back to really exactly the same model that Haldane studied in the 80s. The band structure looks like so. I'm not sure if it's very clearly visible, but there are gaps everywhere at these K points here in the Brillouin zone. And then we project it to the Q plus 1 set. Now, using this Green's function, we calculate using this ground state, we calculate the Green's function. And that's also something that I've done in the lecture course for the simplification of the square lattice. So the Green's function is defined as the time-ordered ground state average of C and C dagger at positions x tau and x prime 0. And then the main point is that these C's and C daggers, they anti-commute with Q. So that means that they don't only excite something in the sector of the fermions, but the C operator also flips the Q on a given site. So it creates an E particle. And as a consequence, there is actually a product, so the Green's function has taken the form of a product of D times G, where G is just a free fermionic Green's function we can evaluate using just this ground state. And this contribution here, which stems from the E particles. So maybe graphically, this is also a picture that I showed in the lecture course. So at a given site, we create a particle But thereby we also create not only a fermion, which is going away, traveling somewhere, we also create an E particle. The E particle is just called gapped. So in imaginary time, its Green's function is e to the minus 2h modulus tau. But it's also ultra local. If I create an E particle here, since in this limit here, this integral limit, the E particle cannot move away, it has to be annihilated at the same point, so we can only have the finite Green's function on site, Cx and Cx. Because if the Cx and the Cx are on the same side, I can bring my product of projectors across these two C's, and the product of projectors does not change. If instead x and x prime were at different sides, I would bring this product of projectors across these two C's, and I would acquire minus sign in one of these projectors, and then I get 0. So the only non-trivial contribution is on site, because these E particles cannot travel in this indubitable limit of the Tory code. And then the Green's function has this form. It is a convolution. So if the free fermions might have a Green's function, is the spectral weight of this G, which is not bold-phased, and might have, it has poles here in green. The convolution leads to a Green's function. So you take this, you Fourier transform it, you get a convolution, you solve the convolution, and then you analytically continue from imaginary time to recurrent Green's function. Take the imaginary part, plot it, get this. What do you get? First of all, the Green's function is ultra-local, so that means that in K space it's completely K independent. So everything here is completely K independent. What you see here is a spectral gap. Spectral gap is essentially between 2h and minus 2h. That's because to insert a particle, you have to pay energy at least 2h. The fermions might be gapless, depending on what these parameters are. But the E particles cost certainly energy 2h, so you have to pay at least 2h. And these guys up here, they are sort of reminiscent of cover bands. Okay, so the imaginary part of the Green's function is already 0 in here. And now also it turns out that the real part of the Green's function is 0 here. Maybe I show this real quick on the blackboard. So when you calculate the on-site Green's function, and now without, you need the on-site Green's function without bold phase. This is integral dk, and then of course this is something like I epsilon minus h of k. Our h of k is just 2 by 2 matrix, so it's actually easy to evaluate this and just multiply it with the same thing here with the minus 1, so I can say like minus I epsilon plus h of k epsilon squared plus h of k squared. This is a number. This is a scalar. This here is an h of k that describes the full dispersion in the full Brion zone. This is the IX. Here, maybe as a reminder, when you solve graphene, you get a contribution which is in the sublattice, which looks like this. Some function s of k. This function itself is odd under certain symmetries here. So when you integrate over k, this s part completely drops. And in this case here, well, one could add in principle, for example, that the topological part, this is this mass that does this here. This is the Haldane mass. But you also see that the Haldane mass is odd under rotating. So integral over k over the whole thing just vanishes. Only the W naught part could potentially contribute, but at this point it's got to W naught equals 0. Okay. So then the full thing is just this full Green's function is just minus I epsilon times some function of epsilon. And this function of epsilon here is gapped. And this here, now I analytically continue from I have to convolve it, etc. But ultimately what's important is just this I epsilon. This is the reason why there is a 0 and 0. Turn direction, there are topological reasons why in König scalators you have to have poles. Sorry, you have to have zeros inside the gap in the one-side Green's function. Okay, so now we've seen that there are zeros which are completely, I mean, we have a band of zeros here. But these zeros, they're non-dispersing because by construction, the model is, you know, everything, the Green's function is perfectly ultra-obvious. E, yeah, that's energy. So here it's called I epsilon because I use, here it's imaginary time. Now what's done here is to analytically continue this to, from Matsubara frequencies to the real axis. And then that's called E, energy. Okay, so yeah, so I said that these guys here are Hubbard bands, and I said that these zeros here are non-dispersive because the model is such that the Green's function is completely ultra-open, so there's no dispersion whatsoever. So we have to perturb about this limit to get any dispersion of the Green's function zeros. So what we add is E-particle hopping. That's a perturbation to the toric code, one of the perturbations that I briefly also discussed in the lecture course. This guy, you see, when it does not commute with the Q. So if there was a Q which was flipped on a given side, the Z term allows the split to go from one side to the other one because Z anti-commutes with the Q term. So if Q was -1 here and +1 here, I make a Z operation here, it flips it to +1 here, -1 here. So that's the E-particle hopping that is added here. And the E-particle hopping graphically can be represented as so. So now I let this guy hop from here to here. And you see, now I have actually also I have if I do perturbation theory in small j over h, I add in leading order in j over h, a nearest neighbor term in the Green's function. This nearest neighbor term in the Green's function, when I Fourier transform it, etc., it gives me a dispersion of these Green's function zeros. If you want, it lifts the degeneracy of the Green's function zeros. It's very hard to see, I think, right? But there are there is a red dispersion here now in this. And in fact, you can calculate the Green's function, let's say, second order in J, and you get corrections. You get a new band structure of zeros here, and this band structure of zeros can either be non-topological, that's represented here by having no inverted gap. It can be topological when the gap is inverted at the K point, or in between it can be critical. And we have the exact expression. I won't go into details. So now this leads to a phase diagram which can be plotted as so. So here we have h over j. So h was the energetic price for an E-particle. J was its kinetic energy, hopping of the E-particle on this axis. And then here we consider W2 over W0. So we solved the model so far that h over j is infinity in perturbation above this limit. At infinity, there are Green's function zeros, but they're independently under the values of W2 over W0. They're non-dispersive, so they cannot be topological Green's function zeros. There's a regime in between here where the W2 is larger than this 27 times W0. But the Green's function zeros are still not sufficiently, the second order hopping is too costly to make them topological. So in this region here, the Green's function zeros are not topological, but out here there is Green's functions zeros which have a topological band structure with an inverted gap. That's one limit where you can solve this problem deductively. A limit where you can solve exactly the perturbation theory. And there is another limit, which is the trivial limit, when j is much larger than h. All of the z's are just pointing into the z direction. That's it. The ground state in the toric code cycle is just a product state. Forget about all of the topological order. And then, of course, this is just a phase diagram of the usual Haldane model. So when W2 is less than this 27 W0, you have a standard insulator, no Hall response, N3, this topological quantity is exactly 0. And when it's larger than this 1 over square root of 27, both of sigma Hall and N3 are 1. We can also calculate N3 now using this, and we find that N3 is 0 here, but we will see in a second again it will be non-zero So this phase diagram, this phase diagram contains essentially four phases, or maybe five. You take this as a separate phase from this one. Essentially, the question is, when W2 is less than W0 times square root of 27, you have no topology in the König bands. When W2 is larger than the square root of 27 W0, you have band topology. And then there's a question. So this is if you wish something like symmetry-protected topological order. And then this is sort of intertwined with intrinsic topological order, whether the toric code sector has topological order, or whether the toric code sector is in its trivial phase. So there are these four phases, and I'll discuss the phase functions.
Can you just repeat again when phase functions are topological?
So the band structure of so let's forget about zeros for a moment. You can just look at the band structure of the Haldane model, and it's topological when you have essentially mass opening at k and k prime, which is opposite in sign. So when W2 is larger than W0, then you have mass opening at k and k prime, which is opposite in sign. When that happens, you actually get, in the case of standard non-interacting fermions, you get a quantized Hall response. You can actually calculate the interval of the very curvature, and you will find it will be this. Okay, and now we sort of transfer this from the poles to the zeros. So you can look at the band of zeros. We have the effective Hamiltonian of zeros, if you wish. And we can look, is this Hamiltonian such that the effective W2 of zeros is larger than the W0 of zeros or not? Yeah. So since we have the Hamiltonian, we can just look at the Hamiltonian. We get the band structure of the zeros. We can calculate the very curvature of zeros. And then we call it topological if the eigenstates of zero. Do you understand, right? So zero means that it means that G inverse of E and K. Let's forget about the imaginary parts, etc. But this guy on group psi of K is some E of K psi of K. Sorry, E of K, this equals 0 is the standard situation. When you have this, you call this a pole, right? It's an on-site excitation. And what we are looking at is this. If you wish, we're looking at this. G of K, psi of K, zeros, equals 0. These are eigenstates at a given energy of K. Now you can ask the question whether these guys here have band structure topology. You can calculate its very connection, you can calculate its very curvature. Okay, so now let's transition. So when you increase the hopping of these E particles, the J becomes larger and larger. At some point, the energy to excite an E particle becomes smaller than the kinetic energy of the E particles. So if you wish, the E particles start to condense, and that drives the transition into this confining, non-topological phase. So what you see here is the E particles actually have two bands, but this is the lower of the two bands. This is the dispersion of the E particles in the Brillouin zone, and at the gamma point, this dispersion hits 0 when the gap is R is 0, which corresponds to H equals 3J and summation. There's a mean field transition from the topological order phase to the non-topological order phase. You calculate the speed of these lines, and in fact, it turns out that while here we have essentially, the Green's function is, the imaginary part of the Green's function is 0. There is no quasi-particle weight when you try to calculate low energies. This quasi-particle weight starts to appear here, and it's nothing but the expectation value of this Z here. If you want the condensate fraction of E particles, which determines the quasi-particle weight of these models. So it's a continuous transition from a mod-like insulator to a regular insulator. And near this transition here, we can study everything in field theory, so in the continuum limit. So we take just the propagator of a continuum model of E particles, and we convolve it with the continuum model of fermions, so just the Dirac Hamiltonian with a mass. And when B and C are equal, this convolution can be taken analytically exactly, so you can calculate the exact Green's function in the regime when you're getting close to this transition, but not yet at the transition. So we can, of course, this is 2 plus 1 dimensions, so we cannot do non-Gaussian fluctuations. This is impossible. But what we can do is we can sort of solve this convolution here at the limit where we have just a Gaussian sort of RPA-like summation of the D. So we get this elephant that I don't expect you to understand, but just to show you that you can calculate the exact Green's function. It contains some very weird functions here. And it's really a non-Fermi liquid-like Green's function. Using this Green's function, we can calculate N3, and we find that N3 is 1 here and 0 here. So we can calculate the topological invariant effect. Then what is plotted here now is the spectral weight as a function of the difference of masses R and M normalized to R plus M. So if you wish, also the energy is normalized to R plus M, and as you know, to excite a physical fermion, we have to excite both the fermion here and an E particle, so we have to pay the price of at least the sum of the two gaps. Therefore, the imaginary part of the Green's function starts only at R plus M. It's the minimal price that you have to pay for an excitation. So below this, the imaginary part of the Green's function. Then what you also see is that so going from right to left here is the same as approaching this transition from above, because R going to 0 corresponds to hitting this line here. This is the Higgs transition. This is the Higgs transition. And what you can see here is the lowest line 0. So you take the determinant of the Green's function, and you try to solve for E equals 0. And the lowest lying energy of 0 is actually increasing. So as you come from above here, the energy of the 0 increases until at some point where R minus M equals 0. That's shown here by this shaded region. At this point, the 0 of the Green's function hits the continuum of excitations, and you will only start finding complex solutions for the zeros. So if you wish, zeros on the left of this point have acquired a finite lifetime. So there is no more real solution epsilon of k, such that the determinant of g of epsilon k, comma k equals 0. We can also calculate with this. We can calculate here you see again the crosscuts of the spectral weight. So you see that there is a gap. Then you see that over here the spectral weight sort of goes down, while here the spectral weight starts to pile up. This is the precursor of the quasi-particle weight that's hitting in here. And as I said, in this regime over here, the imaginary part of the energy of the Green's function 0 starts to appear once it. Okay. Then from these transitions that we have here, we can actually infer what type of edge states we have, depending on what type of interface. For example, interface standard between topological insulator and insulator, there's an edge state. We know that at the interface between this region called ZTI and anything that has N3 equals 0, there is an edge 0 that's moving around, so we actually can also find that. And in particular, also between here and here, sorry. So when you bring a topological insulator with zeros close to topological insulator with poles, at their interface, sorry, there is a region where it is a semi-classical ground, so you expect very similar physics to this appearance of finite lifetime. So the zeros get actually pushed up, and then here the zero has, the zero has finite lifetime, so that this is just no low energy features and an interface between a topological insulator with zeros and a topological insulator with poles. Yeah, 5 minutes left. If you want to know how to probe these, we discussed this in the question session. And instead I just go to the acknowledgements. So most of what I showed you was done together with Stefan Bormann, who's a PhD student at the MPI, Chandan Sethi at Rice, and Urban Seifert, who just moved from from Santa Barbara to Cologne. The first part that I showed you, this numerics, was done by everybody who read here, and related works were done with the green people. And since I told you that this is a seminar on existentialism, I thought it's worthwhile just to end